All right, bit of a change of gears here. Ilia Larchenko, is that correct? Yes, from Agoda is going to talk to us about the LeRobot library for bridging AI and robotics. What could possibly go wrong?
Yeah, thank you. Good morning, everybody. I'm Ilia. I'm really glad to be here. And today I will talk about the robotics and AI and how can you experiment with the kind of intersection of these two fields using some open source tools, even at home, basically. So before I begin, a couple of words about myself. So again, my name is Ilia. I'm currently a data science director in Agoda, and here I live here in Bangkok, in Thailand. I have a bit more than 12 years of experience in machine learning, data science, analytics, and connected areas. I used to be pretty active on machine learning competitions in the past. But today, the topic that I'm going to talk is not kind of directly related to my work, but related to my hobby. So I've been doing robotics as a hobby for quite a few years already, in and out. And yeah, this presentation will be more like from the hobbyist perspective rather than from the professional from the robotics field. And before I begin, just wanna understand the audience a little bit better. So please raise your hand if you ever try to do anything related to robotics. So okay, nice, quite a few people. And now the same question about like machine learning and AI. So who ever trained any machine learning model themselves? Okay, great. So we have quite a few people who did it. So let me begin. And first of all, just want to give you like very quick overview about the overall approach to robotics. So I would say generally, historically, whenever you wanted to teach a robot to do some autonomous things, you use this what's called classic approach, when the algorithm of the robot has three main steps. It's perception, planning, and control. So perception step is when you take some raw sensor data. It can be, I don't know, some either some sensors, so let's say pictures from the camera, and then process it into something more interpretable. So let's say if you're controlling some robot arm, you want to grab some objects, so you take the picture and recognize what are the coordinates of this object on this picture. The next next step is usually planning, when you take this data and kind of create the high-level plan for the robot. So let's say, okay, if this object is on the right, then obviously robot should move to the right. And finally, the control step is when you take this plan and transform it into the actual actions for the robot. And in robotics, actions usually means positions or velocity of all the motors in the robot in most of the cases. Again, it's very, very high level, but many applications, many approaches to robotics, they work like this. They have these three steps or something similar to this. But recently there is a rise of end-to-end robotics, when it's a little bit different paradigm, where you combine this perception, planning, and control steps into one policy, one model that is usually AI or machine learning model that simply takes raw observations from the environment and directly predict actions. So instead of having some separated steps, let's say it takes pictures from the cameras and predict directly motor positions of the robot. And it's very interesting area that is rising right now. So if you search for in YouTube for some robotics demo, you will see in the last few years there were a lot of breakthroughs in this area and a lot of very, very cool things that robot learn to do using this approach. And today I want to introduce you LeRobot library. It's a library that allows you to do the whole cycle of experimentation in this end-to-end robotics. So this library is developed by Hugging Face. It's a well-known company in the area of open source machine learning, probably one of the biggest players in the market. And LeRobot is basically the robotic initiative. And currently, this library allows to do the whole cycle of robotic experiments. It allows you to control robot through teleoperation, collect data set, train state-of-the-art models to control a robot, deal with simulated environments, and so on. And in this presentation, I will basically go step by step through all of these things that I mentioned. So let's say you want to do robotics, and probably the first thing you need is robot. So let me introduce this robot to you. It's called Standard Open ARM 100 robot. And it's developed by the Robot Studio, and it's completely open-sourced robotic arm. It has 5 degrees of freedom. Most of the parts are 3D printed, so the only thing that you need to buy is like 6 motors and 1 motor controller. And the main kind of advantage of this robot is that it's very cheap. So it costs around $130 per arm with everything included, and it's way cheaper than usual robotic manipulators. So for example, some manipulators that usually used in research, they can cost like few $1,000s. Some industrial ones that like heavy things, they can cost like tens of thousands of dollars, but this one is like very small, cheap, and affordable. Of course, it's not as strong. Of course, it's not as precise, but it's more than enough to run AI experiments, simple AI experiments at home using robotics. And yeah, I will talk about it on the next slides. So as I said, most of it is 3D printed. So basically, you need maybe like 20 hours to print all the parts of this robot, depending on your printer, of course. And then maybe around 1 hour to actually assemble this robot. You can see some video of me doing it. It's actually a pretty fun process, but if you kind of don't like it or like you're not good at it, even so it's actually pretty easy when you follow the instruction. But again, if you don't want to, you can always skip this process because there are already companies that sell pre-assembled or at least printed robots. So there are, again, easy way to pay a little bit more and get it's already assembled, but I don't know, from my perspective, it's pretty fun to assemble it yourself. And the next thing that you can do is actually modify your robot. So on this picture, you can see what modifications I did. So this robot that I brought today is kind of vanilla version. But when I run my experiments at home, I use a little bit modified one. So I added a couple of cameras to it. One camera is like a wide lens camera on the wrist of the robot. It's a view on the grasped object. One camera is on the bottom, that is forward-looking camera. And I also replaced the gripper. I think this one that I'm using like a bit more convenient than the one in the original robot. But the main point is that, yeah, you can make a lot of modifications yourself, and community is also doing a lot of modifications. So if you join like Discord group or just search for what people are doing with these robots, you can find they do a lot of extra 3D printed parts. There are many different grippers already available. There are many different modifications of robots when people add 1 extra degree of freedom, 1 extra wrist to the robot to make it more convenient. So yeah, there are always some modifications that are being released. And of course, you can use them. You can use your own modifications. And I think it's one of the like fun parts of robotics. So like on top of some flexibility in software, you have some flexibility in hardware, and there are like more degrees of freedom that you can experiment with. So the next thing, after you assembled your robot, you somehow want to control it. Before it learns to do stuff autonomously, you should be able to control it manually. And by default, the way to control this robot is to use another robot. So I have another second robot here. And if you look at it, it's almost the same as the first one. So they're almost identical. The color choice is just depending on what you used for printing, so it's not the difference. But the only difference between them is this robot, instead of gripper, has this convenient handle with trigger. And the idea is you can use one robot to control another. So basically, all the 6 motors that you have in the robot have encoders. It means that at any point in time, you can say what is the current position of the robot, current position of each motor. And this teleoperation that you can see on the video is extremely simple. So you move one robot, you read the positions of all motors, and you send these positions as actions, so it's like targets for the another robot, and just move all the motors of the second robot to the same positions. So eventually you can see that on the video, red robot can mimic all the movements of the yellow robot. It's actually pretty convenient. It's very easy to learn when you do it like few times, then you know how to control it. You can do it pretty precisely. So it's a very convenient way to control your robot. The main problem of this approach is that you need a second robot. So basically, you need to spend 2 times more money to control your robot, and it's not nice. So this is why, again, community, including myself, developing other alternative approaches to control it. For example, these are my experiments with integrating PlayStation 4 controller into this robot. And so yeah, basically you can control your robot with this controller. There are a few different modes. So on the left, you can see that I just use joysticks and arrow sticks to move the robot a little bit in different directions. On the middle one, you can see that when I press the button, like right now, it moves to some preset locations. And also you can see that sometimes it's like blinking with red, and you cannot see, but it's also vibrating whenever you reach the limits. So when the robot cannot go down more, or like cannot open the gripper more than you are trying to open, it has some feedback. And finally on the right, you can see that you can also control the robot with accelerometer of your PlayStation controller. So basically rotate your controller, and the kind of gripper will rotate the same way. So these are like my experiments. This is what I did at home. There are many others. So again, in community, I think I've seen maybe all possible game controllers, game pads were used to control this robot. I've seen people implemented some convenient control with touchpad and keyboard. I even seen people doing like control using your gestures. So when you just hold your hand in front of the camera, move your fingers, and robot like follows the same movements. So there are pros and cons of all of them. But yeah, the idea is that you can always save a little bit by controlling it in an alternative way. To be honest, I still think that controlling it with this leader follower arm approach is probably the most precise and convenient. But again, there are alternative ways, and yeah, people keep exploring them. So when you assembled everything, when you have like the way to control your robot, you need to set up your environment for experiments. And again, as I said, I'm not working in robotics lab. I'm just doing experiments at home. So this is my dining table in like my condo here in Bangkok. So I set up the experimentation environment there. So on the left, you can see the follower arm, the red one. On the right, you can see the leader arm that is used to control. It's very important to keep the leader arm outside of view of all the cameras. Otherwise, it will learn to just repeat your actions of leader arm instead of doing some reasonable stuff. And then you can also see I added one more camera. I have like top view camera that provides some strategic view on the whole area where you do your like actions, your experiments. And finally, I have like laptop and 1,000 wires that connect in all these things. And yeah, this is where I run my experiments. This is where I do some tests with my robot. Yeah, so when you have everything set up, the next step is to collect data set. And when I talk about data set in robotics, and again, for this particular behavior cloning example, each episode in your data set is just recording of you teleoperating the robot to complete the target task. So in this example, the target task is to like grab the ball and put it inside the cap. It's pretty simple. And I'm teleoperating robot right now, so it's not in the camera, but I'm somewhere nearby with this leader robot, with this leader arm, controlling this one to put this ball inside the cap. And each episode is just recording from all the cameras, so you can see like 3 camera views. And also you can see 2 charts on top. So they look pretty similar. So each chart has 6 lines on it. And basically, chart on the left is action chart. And it represents the positions of all 6 motors of this leader arm at any point of time. And the chart on the right is state chart. So it represents positions of 6 motors of this like follower arm at any point in time. And as I said, the kind of position of the first robot is the targets for positions for the second one. So these charts are pretty much aligned, but you can see that there are always some differences. They're not like exactly the same because there is some delay, there is some inaccuracy in the movements and so on. But this is how the data set looks like, how one record in the data set looks like. And if you want your robot to do some simple task like the one that I demonstrate here, you need maybe like 50 or like around 50 demonstrations like this to be able to train it and make it work autonomously. Another important things that is also available in this library is integration with simulated environments. So I think many people, when they think about robotics, they think that you always deal with the real robots, always deal with like hardware robots. But in practice, a lot of things in robotics are done in simulated environments. It's much cheaper, it's reproducible, it's much easier to experiment in these environments and so on. And most of the research is done in simulations, and then on like later stages, you really move to the real robot. So this is a very important part of the whole cycle of robotics development. And yeah, again, this library, LeRobot library, is integrated with a couple of, with like few of famous simulated environments. Some of them like simple two-dimensional ones like this PushT on the left. Some of them actually simulate the whole robot with 2 arms and trying to do like some task of inserting like one object inside another. So yeah, it's very, very interesting. You can also use some human collected data sets in these environments to train your model and validate it against some existing benchmarks. So let's say you collect a data set either in the virtual environment, like simulated environment, or from the real robot, and then you want to train the model. So the interesting thing, again, if you don't have a lot of experience in machine learning and you don't know how to train models, it's still fine. Again, this LeRobot library provides you some training scripts where you can simply like run something like this snippet of code, just provide the data set, provide the like type of the model or policy that you want to use, and it will train your model overnight automatically without a lot of interaction. So a lot of intervention from your side. It's also automatically integrated with weights and biases monitoring service, so you can see out of the box, you already can see all these charts and all the monitoring during your training. That is very also convenient to be able to check that the training happening easily. When you train this model on the like real data set, you maybe need to specify extra like few parameters, but again, it's usually as easy as this one. So on the other hand, if you are interested in the machine learning part, in the algorithmic part, as I do, as I said, like most of my professional experience is around ML, so I was very interested to look into the details, how algorithms are working and so on. So you can also kind of go deeper and you can experiment with the policies and the algorithms. I did a lot of experiments. I tried my own architecture of the models, and to be honest, a bit surprisingly, I even managed to achieve state-of-the-art results on this 2 particular simulated environments. So I developed the like approach, very pretty simple architecture that is much more like streamlined and simpler and smaller than other existing state-of-the-art approaches. And on these 2 particular environments, it managed to significantly beat the like success rate of the previously best approaches. That is kind of, again, a bit surprising for me, but it kind of shows that there is a lot of space for improvement. So I think it's like very fast developing area, and there are still a lot of things that you can contribute. I think most of the algorithms that I used right now, they're far from optimal, and like a lot of things can be still improved. So yeah, if you're interested to kind of contribute a little bit to the algorithmic side of this, then you can always do it, and I think there are still a lot of space for you to do it. And finally, after you train the model, you you can run it on the real robot. And on this video, you can see the robot completely autonomously completing the same task. So it's looking at all the cameras that it has, and it's basically autonomously based only on the camera images, tries to put this ball into the cap, and you can see that it's usually successfully do these tasks. And on the right, you can even see that my policy is also pretty stable. So when I change environment, when I move this cap, it's still following it. It's not getting stuck. So yeah, it's pretty cool. And this is how it works for the simple problems. And of course, it's like slightly cherry picked because I don't show any fails on this videos. There are fails sometimes. Sometimes it cannot grab the ball. Sometimes it just freezes in positions like this when it's like almost put it to the cap and just freezes forever. So it happens, but for at least for this simple task, you can achieve very, very high success rate. So it's pretty close to reality how it works. So yeah, this is the whole cycle of experiments that you can do. And again, you can simply do it at home. You need like $100, let's say $50, and you can start experimentation at home. You can contribute to algorithms. You can contribute to the hardware. So it's pretty fun and interesting. I highly recommend you to do it. And just before I finish, just want to say that very nice thing about this library and the community about it is that this community is very active. So if you especially like, you can follow like Twitter, but you can also join Discord of this library and see that there are a lot of developments going on. And here I just want to show you just a couple of announcements that happened like in the last months. So it's basically what was released in February. So one of them is LeKiwi, developed by University of Illinois. It's basically mobile version of this ARM. So they added some platforms, some wheels, made it work with Raspberry Pi and so on, and get this robot that can also like move in space. And it's controlled by the same algorithms, so you can use the same completely like approach to train this model. Another one is Pi0. So this announcement of Hugging Face team actually porting Pi0 model into LeRobot library. So Pi0 is kind of more complicated edge kind of development model in robotics. It's, I would say it like some analog of probably LLMs. So imagine like ChatGPT that instead of predicting tokens, instead of predicting words, ChatGPT can predict actions for the robot. So this is what VLA models are. So it's like a big model that takes as input your natural language commands, take images from camera, and then predicts the actual actions for the robot and manage to control your robot. So it's like edge research. It's very cool. And again, it's already integrated into the library. So yeah, this is everything I wanted to say today. So please like follow this library and different like GitHub and everything else. You can also follow me to ask any questions that you have. Yeah, thank you. Thank you very much. Thank you very much for your attention.
Thank you, Ilia. I have a question, but I'll ask audience questions first. But before that, is Apurv Garg in the room, please? Can you please set up and get your slides onto the screen now while we do the Q&A? Right. Questions? Excellent.
The slide where you showed the manual training part, like you had like the action and the target, right? But then it sounded, yeah, this one. Mm-hmm. I don't know, the way you explained it, it sounded like that the action is also used as an input for the trained model, but I thought it's mostly just the sensors, or I don't know, maybe you can explain that.
Yeah. So the pictures that you see from the camera and the actual state of the robot, like historical, like current state, is used as input for the model. Yeah. But actions used as target. So the model, at least like this model that I use, tries to predict, like, let's say, next 10 actions given the like state and given the pictures that you have from camera. Yeah, I think you can just close it and prepare. Yeah, so yeah, this state is input, actions is actually output that is trying to predict. So it's like try to predict what I will do in the next second as a person who controls this robot. Combined with camera, like camera and state are the main inputs for the model. Yeah.
Nope, maybe not.
Hello. Thank you so much for sharing your hobby. I have a question. Is it possible to prepare data set from a simulator environment and after this use a real model? What is the successful rate? I mean, like, what is the difference will be? I hope clear.
Yeah, it's a good question. And actually, this is how it actually works quite often. So a lot of robotics labs, they create this simulated environment. There is like, I don't know, NVIDIA has like very big project where they create like physical world simulated to train their robots. And this is very popular approach to actually train the robots. So you mostly train it in simulated environment, and then either without any adaptation, you kind of put it into real world, or sometimes with like some extra fine tuning, you put it into real world, and it's much easier and better. I didn't try it yet, so like I didn't try to experiment with this particular robot and simulation of it, even so there are already some of them available. But yeah, usually, of course, when you move from simulated environments to real world, the success rate drops. But if you add extra fine tuning, extra training, and like a little bit of data in the real world, it works well. So this is how it's often done.
I think there's one behind you. We still have several minutes, and we've got some technical issues. So there's I think this gentleman here had a question. Use the microphone, please.
I missed the beginning, but the type of tracking you can do, is that limited by the hardware? Can you only really do like event detection-based tracking, so like fully just one object, and it's just whatever object's there, it has to find that one, or it can't? If you have like multiple objects, some of them maybe get obfuscated or something. Is that within the scope of what it can do, or is it detection based?
Yeah, sure. So it can do, it's definitely within the scope. It can require you maybe train a little bit bigger model. So I train it for simple tasks, and I use very simple and relatively small models for this. If you want to train it for like more complicated problem where like some objects are like obfuscated and so on and so forth, it also will work. So we probably need a bigger model. You probably need like a bit more data, but there is no reasons for it not to work. And yeah, so I try to run it for a bit more complicated problems, and it works fine. But again, when you make it harder and harder and harder, of course, success rates start dropping, and you need like more tweaks, more fixes to make it work. But yeah, it's possible. It's possible.
We've got about 3 minutes before we start the next session, in which case I'm going to ask a question.
Yeah, sure.
You mentioned in passing, but I missed it if you expanded it. When you're going through that initial training cycle, you mentioned that it was important that something, perhaps the cameras, cannot see the manual guidance input. You want to talk a little bit about that and how that can go wrong?
Yeah, sure. So the cameras, so the robot relies on the camera pictures to predict like next actions. And the thing is that if you, let's say, just stand with this, like the leader arm in front of the camera, and your movements are on the camera, then it's much easier for robot to just learn to recognize the position of the leader arm from the picture and just repeat it, rather than understand that it needs to grab the ball and so on. So just seeing you moving the arm and learn that, oh, I just need to do the same. And then it learns to kind of mimic the movement of your leader arm from the picture, rather than like completing the actual task itself. So I've seen people like, again, in some discussions, people made this mistake, and they really like train the model, and they say, oh, it is doing nothing unless I start moving this arm again, and then it like just mimic the actions of this arm. So
right, so there's a bit of learning about controlling the limbs, which is learning either way, but there's a sort of task planning that it doesn't learn if you do this for it.
Yes. Well, just much easier to replicate your actions that it see on the video, rather than trying to complete the real task.
Brilliant. Okay. That I get. It's like with a child doing the thing for them instead of letting them struggle a bit with how to do the thing.
Yes.
So yeah, that works really well. Thank you so much.
Thank you.